Hello and welcome back to Calculus 1, section 311, part 2, related rates. Last time we talked about the idea of relating rates so that we can compute change in time. So today I'm going to work on more of these concepts, but before we go and do more, last class we've seen squares, we've seen triangles, and you are familiar with those formulas. From the experience, I learned that once you see volume, you tend to lose your cool. So let's talk about volume formulas, because you need to know all of area and all of the volume in order to perform these problems. Remember, no formula sheet. So let's talk about all of this mathematics in general. You have length, which is one-dimensional. Then you have area, which is two-dimensional. Then you have volume, which is three-dimensional. Then bulk, four-dimensional. And you can go as high up as you want. We are going to stick with these. So your problems will most likely involve either the first two or the first and the third. That's how the problems are linked. Rarely you will see the link between the two. You can link these two as well. Now, areas, you guys should be good with those. You know, area of the square, area of the triangle, area of the rectangle, area of the circle. So all of those formulas are known to you. Volume might be trickier because you don't have as much practice with those. And then also you probably try to learn each volume separately without classifying those, which makes everything hard. I'm going to classify all of the volume into three groups. The first group is the group of prism objects. So we can talk about a box or a cylinder. You see that the top and the bottom are parallel. They are flat surfaces. And volume of all of these objects is always area of the base times the height. So you have area of the base, whether it's a square, rectangle, triangle, circle, whatever that area is, area of the base. You can have anything in there. The second category of objects are objects which I like to call spiky objects, which are going to be pyramids, cones, anything that would have this spike at the top. And these are some of the most famous. There, obviously, you can draw this pyramid with triangle on the bottom, whatever else. And the volume of what I call spiky object, the volume for that would be 1/3 base times the height. All of them fall under that category. So you are not going to memorize three-sided pyramid formula and then the four-sided pyramid and then the eight-sided pyramid and then the cone. They're all the same. If you know the volume of the base, you will multiply that with the height, If it's a spiky object, you also multiply with 1/3 and you're done. The only object that doesn't fit in any of these categories is going to be the perfect object. And the perfect object is? Yes. Sphere. Sphere is the perfect object, and a sphere has the volume so sphere four-thirds pi r cubed, something you get to prove in Calculus 3. You can also prove it in Calc 2. So you see that these two are pretty much the same. It's 1/3 in front, and this is the one that it's different than all of them. So now we can create a problem. So what the person on the top of the hill is going to do is standard stuff in cartoons, right? Drop a snowball. What happens? Yeah. So the snowball will roll down the hill. Right? So, as the snowball rolls in time, it picks up the volume. What are all of the concepts that grow in time? Radius, surface area, and volume. So, we can say that we start with the snowball. So small snowball. Which we drop down the hill. So we can ask, what is the change in volume, which would actually be the size. So what is the change in volume as the radius grows at the rate of, let's say, I don't know, 10 inches cubed per minute, whatever. When the radius, can't spell this morning, is, let's say, 20 inches. It's a large snowball. Well, it went down the hill. the way you do all of these problems is you look at the geometry of the problem first. We are dealing with sphere, therefore so concepts we are dealing with are sphere and volume. That immediately triggers formula for 4/3 pi r cubed. Doesn't matter which order you put it in, but it's the standard. And now we are looking for the rate of change of volume in time. We are given the rate of change of the radius, and we are also given the radius. First, you have to make sure that these units are the same. If I give you 1 in feet and 1 in inches, you have to convert one or the other. You cannot just mix all of the different units. To solve this problem, we know that we have to take the derivative in respect to time, because we are looking for the change in time. So, the derivative of volume is dv dt. On the other side, 4/3 pi is a constant, and the derivative of r cubed is 3r squared dr dt. So hopefully you are remembering from your last class that we have to use the chain rule every time when we take the derivative of a variable that doesn't match the variable we are taking the derivative in respect to. We are taking the derivative in respect to t. Neither of the variables v or r are t. So we have a dimension mismatch, which means we have to follow with the chain. Now 3 and 3 cancel, and we are left with a related rates formula, which we use to solve the problem. 4 pi r squared dr dt. We are looking for dv dt. So dv dt we're looking for is 4 pi 20 squared. That's the radius times 10. So that's 400 times 4 is 1600 times 10. Right? Inches cubed per minute. Wow, I said radius grows with inches cubed. No, radius is just inches. Fix that. Radius is length. So we calculated that it's picking up, and then 16 times 3, right, which is some pi, almost 3. So it's picking up almost 50,000 inches cubed of snow per minute. So that was a sphere problem. What else can we talk about? Inflating or deflating weather balloons, right? They're also spherical. I don't know, whatever they have in the melting snowball balloons. So you can also talk about melting, right? In which case you would use minus. Great, so these are all the problems that we have for sphere. The next problem is, in my opinion, really interesting. I watch a lot of these SpaceX and NASA, launches. It's interesting. It's for a few minutes. It doesn't take a long time. Every time, it's just everything is shaking, and the shots are terrible, and the camera is all over the place. It's a simple thing to fix. Design a little circuit and program it with the equation we can derive using this section, and you have automated camera that has the perfect shot every time. So let's take a look at that. So here's the Mother Earth. I'll put the rocket over here. Ah, that's fine. Well, it's a rocket. Yeah, SpaceX. And the rocket is going to shoot straight up. Now, some distance away, we're going to place the camera. Look at that high-tech camera. The camera is going to be on a hinge with a servo motor that can rotate this camera right this way. So if the initial shot of the camera is there, as the camera picks up the other angles, right, it's gonna go like that, up and so on. So the camera is going to shoot straight and then swing the angle theta. As the rocket is moving up, the camera will automatically follow the rocket. You want to figure out mathematical function that you have to program into the controller so that rocket is always in the middle of the shot. Can you do that with a constant motion? No. Why not? Yes. So the rocket is going to start slowly, right? Needs to go 7 miles per second to escape Earth's gravity. 7 miles per second. How much is 7 miles per second? That means that you are in New York in 10 seconds from RVCC. That's how much that is. 7 miles per second. Awesome, right? So this camera needs to rotate slowly, right? But at the beginning, the camera is closer to the rocket, so it needs to shoot up with the rocket, and then as the rocket is picking up speed, right, needs to move faster. So let's take a look at what we have. Clearly there is a height edge that we have to worry about. We can put this 1,000 feet away, right, so it doesn't get obliterated by the fire and stuff. And we have this angle that we are looking for, because we are technically looking for angular velocity omega. Now, you call that omega in physics, or we can also call it change in angle over time, because for circular motion, your path is angle. The derivative of path, which was angle, is angular velocity, and then another derivative of that would be angular acceleration, which is alpha. We're not going to use it here. So now we have this geometry. Now, what type of equation should I write? First, what is the geometry that we have? Right angle triangle. Good. Right angle triangle. What are the 5 concepts we talked about regarding the right angle triangle? What formulas, concepts can we associate with that? So Pythagorean theorem. Do we get to use Pythagorean theorem here? No. All right, good. Another concept. Sine and cosine and tangent and so on. Do we get to use that one? Yeah, because we have the angle. What are the other ones for triangle? Which one? What other concepts about triangles you know? Don't look at the picture. Just tell me what other concepts you know about triangles. We said Pythagorean theorem. We said all of the trigonometry. What else? Area. We talked about it last class. Area. But we don't get to use that one either. And what else? The triangle? What else? Perimeter, guys. Perimeter. But we don't use that one either. If you know all of them, then by process of elimination you get to which one you actually need to use. So we don't use the volume. Volume. You plagued me now. Get out. We don't get to use area. We don't get to use perimeter. We don't get to use Pythagorean theorem in this case because we have angle. We use trig. Great. By process of elimination, we got to the part where we use trig. Now, which trig function do we get to use out of 6 of them? In the way this is set up. Tangent, very good. It's tangent because it's opposite, which is age, divided by adjacent, which is 1,000. Great. So we get to write tangent theta is equal to age over 1,000, from where age is equal to 1,000 tangent theta. Now, what concept do we need? We need the concept of d theta dt. So what do we have to do to get d theta dt? Exactly, differentiate in respect to time. When we differentiate in respect to time, we get dh dt is equal to 1,000. What's the derivative of tangent theta? Secant squared theta. And then follow with a chain d theta dt. So now you see all of the features that we need. Now what's dh dt as a concept on our picture? Very good. dh dt is the speed of the rocket. Nice. And d theta dt is angular speed at which the camera rotates. Now, we know that the camera is going to rotate from 0 degrees to 90 degrees. We can partition by a degree, or we can partition and then ask computer to calculate at each degree, each half a degree, depending on the precision and smoothness that you can afford. For servo motors, that size might be expensive. So you now just write the software. You can write the software. You have the equation. The d theta dt, which is what you're looking for, is going to be dh dt divided by 1,000 secant squared theta. Now, secant squared in the denominator is a cosine in the numerator. So d theta dt is equal to 1 over 1,000 cosine squared theta dh dt. And there you go. This is engineering, guys. This is 100% engineering. You understand what kind of concepts you need to put the stuff together, write some equations, figure things out, and then you simply write the code. It's everything about code today. Code, 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 code. If you're not coding, is problem. So now, what you do is you plug all of this, make the array from 1 to 90, 0 to 90 for the angles, get the calculation going, and dh dt, you have to constantly input that, scan that data, but we know how fast the rocket is going. That's the information that we have at every point in time. So all of that information fed into the equation tells you the speed at which the camera should rotate, right? So that's fast omega, right? And it's slow omega. And we have a variable omega. It will all depend on the ways, right, all of these things combine. The HTT will grow fast. Cosine squared will die out, right? Because it's, as theta goes to 90, cosine is plunging to 0. So what we see also is that when the angle is 90 degrees, the camera is going to stop, right? Because the motion is going to stop. Because d theta dt becomes 0 because this is 0. And 0 is our everything, speed is 0, so it's going to start fast and it's going to keep slowing down. And now we can actually graph this function and figure things out. So it is possible to create something that will nicely give you the shot for the launch. The program equation. Now, obviously, if I say, okay, so what is the speed, right? What's the angular velocity at 45 degrees as the rocket is going 5.9 miles per second? You will plug those values in and you will give the answer. The most important part is to realize the geometry and then pick the right formula. And for that, you either have to be mentally present when you read the problem. You have to be focused. If the problem mentions volume, it's a volume equation. If the problem mentions area, it's area equation. If there is a triangle, well, it's perimeter, area, Pythagorean theorem, or one of the 6 trig functions. There are no other concept. The toolbox is finite. It's just what, if you are willing to classify all of that, sit down and learn them systematically one by one. So those are that will be that type of the question. Let's see what else cool thing we can do. Ooh, more engineering. So we have a conveyor belt, some sand is coming down a conveyor belt, and it falls onto a conical pile. So sand or small rocks, something, right? And it's not hard to picture this. What happens in time? Pile grows. But as you can see, right, as it grows inside in all directions. Becomes wider and taller. So when you're considering this type of a growth, right, you can you have to consider the radius and the height. Now, sand pile. I'm obviously talking about the volume. It makes no sense to talk about anything else. We are definitely talking about the volume here, because it's how much rocks do you have on the pile? How much sand do you have on the pile? So what you do is you say, oh, that was a spiky object, so volume is 1/3 base times the height. And what's the base? Circle. So the volume equation for this must be 1/3 pi r squared h. You make this formula. You don't memorize it, you make it. Spiky object, circle in a base, times the height. It's very systematic if you sit down and learn. Now, when I write the volume for something like this, I stop and think, what are the variables that I have? And a variable is whatever is changing as the time goes on. So think, is the volume changing in time? Yes, we have more sand, more rocks, whatever. Is the radius changing in time? Yes, because it's becoming wider. Is the height changing in time? Yes. All three letters that we have are variables. So what happens is you take the derivative. What happens here? Product rule. Product rule happens because you have a variable times a variable, or a function times a function, and you know that's a product rule. So now, as you take your derivative in respect to time, the change in volume in time, which is dv dt, is pi over 3, which is a constant. And now what do I get as a product rule inside? Copy the first times derivative of the second plus copy the second times derivative of the first. Observe that I have dh dt, dr dt, dv dt. I have three variables, and because I have three variables, I better have three rates, because I take the derivative of the entire equation. So now we see that we have the change in volume, change in height, and change in radius. What you get in this equation must reflect physical reality. Otherwise, the model is garbage. You have to have change in radius and change in height, because they are both changing in time, and obviously change in volume, which is the VDT, because the volume grows in time. So now you have all of those concepts. And how many unknown values do you have now? And the answer is 5. The dv dt is one of the unknowns, radius, the h dt, age, and the r dt. There are 5 unknown, which means that you better be given 4, or means to find whatever it's missing, and then the 5th one can be calculated. Now, the rate of change of volume in time. That means how fast you are piling up the sand. From engineering point of view, right? It's a very important question because you want to shut off this conveyor belt before the sand starts piling up on top of it and breaks it. It's extremely expensive to fix those kind of things. So there has to be a shut-off mechanism. So you either sit down and once design a system that will shut it off, or you continuously pay someone to look at it and then go click. It's the entire job, right? Pay year round, click. So clearly we're going to design a system that will automate this. Now what do you need? You need this equation solved, right? So what can I get? What would I be concerned with? Well, generally, I would like to be concerned. The book has this problem in a little bit simpler form. Generally, I want to be concerned with the height because I don't want this sand to reach the conveyor belt, because as soon as it reaches conveyor belt, it's going to start piling up because there's nowhere else to go. It's going to start piling up on the conveyor belt and break it. So generally, if I'm writing these problems, I like that to be unknown, because primarily we should be concerned with the height. Good. Now, I know what is my production rate, and that is the rate of incoming sand. I know how much sand per volume, right? Volume is coming in on the belt. So I can say that the rate of change is whatever the rate of change of incoming sand is. Maybe I can steal some. Maybe I can steal some of the numbers from one of the exercises if they have. I don't think they have anything. And I can make up stuff too. 120 feet cube per minute. So rate of incoming sand is 120 feet cube per minute. And we also can say that the instant we are looking at when height is, they give us 10 feet tall. So height is 10 feet tall. That's 10 5. And we also need another piece of information about the geometry of the entire thing so that we can actually do the problem. And that is either the rate at which the r dt, or which is the change in radius, or because if you take a look, what we have is we have this, we are looking for this, so that's okay. We have this, and I still have r and dr dt unknown, and that's the problem. We can't solve everything this way. Now the book goes with a cheaper type of problem and says that the radius is always 3 times its height. Radius is always 3 times its height. So the book gives this piece of information as a link. So how we use all of this now? Well, I'm going to draw a cross section here. And then here. Sand is coming in from this direction, and I'm just drawing half of the cross section. So if you cut through, you will get a isosceles triangle. And then I'm just looking at the half, because these are the heights that I worry about, and these are the radius things that I worry about. So I can call this height and everything capital height, and I can call this radius and everything capital radius. So what I know is that the ratio of radius and the height is 1 to 3. Now, if I differentiate, I get the ratio of the speeds of their growth. So dr dt is 3 dh dt. So what do we do with this now? We can plug everything into the equation. We have all of the information necessary. If I combine 10 feet right there, what I get is r is equal to 30. When height is 10 feet, using the fact that the height is always 3 times less than the radius, 10 times 3 is 30. I have everything that I need to plug in the main equation. So I'll write main equation one more time. So dv dt is equal to pi over 3 r squared dh dt plus, now I can nicely write this, 2hr dr dt. I have that this is 120 pi over 3. I know that r is 30, so 30 squared. Dh dt is what I'm looking for, so I'll happily leave that in. Plus 2 times, and the height is 10, and the radius is 30, and the r dt is given by 3 dh dt. And now if you carefully look at this, the only unknown variable is dh dt. So we have 360 over pi is equal to 900 dh dt plus 1800 dh dt. Right, that's 90, 900 times 2, 1800. 360 over pi is equal to, when you add these two, 2700 dh dt, and finally get dh dt alone, which means 360 over pi times 1 over 2700. 0 dies instantly. Both 36 and 27 are divisible by 9, so I have 4 over pi times 1 over 30. So the whole thing is 4 over 30 pi. 4 over 30 pi. What? It's going to be feet per, what are the units? I'm trying to see what they gave us in the book. Minute, yes. So the h dt is 4 over 30 pi feet per minute. Now, I said this was the easier version of the problem. Why was it easier? Because this was given to you, this relationship. I was given in a text. Generally, you have to figure that relationship out when you look at the similar triangles. So when you look at other cone problems, if you run into a situation where this relationship is not given to you, remember that I told you about this triangle. Try to set it up. If you get stuck, make sure you ask, and I can work out that problem so you can see that setup. The rest of the problem is identical. One more problem, and then we're done with this section, and we'll talk about the exam. So let's consider soda can. We know that a soda can is a cylinder. Now I keep forgetting to measure the. I keep forgetting to measure the units, the measurements of it. So let's approximate again. What would the radius of the soda can? I would just like to compute the volumetric difference between two of you. What is the radius of the soda can? Two inches? Easier to use two, right?
Wouldn't that mean that a soda can is 4 inches wide?
Yeah. Is that bad? Alright, fine. I'm going to Google dimensions of soda can. Oh, kill me now. 4.83 inches high and 2.13 inches in diameter. Ha! So I'm going to use 2 and 5. Now, we're going to put some liquid inside. Well, I know you like unnatural. What? Colors, so let's use green. Do? Alright. And we're going to have this a blue straw, right? And as you drink, the height goes down. So we have dH dt this way. Now, as you drink, what mathematical concept are you taking away as you drink? Volume. So now I should, I guess, Google, yeah, how much is one? What should I even? 33 centiliters? Okay. Two inches cubed. Let's see. That's a 20. That was nice. That's nice. 20. So 20 cubic inch. So let's say you will take a sip every minute, whatever. So we have dV dt is equal to negative 20 inches cubed per minute. And this is how you mathematically say that you're drinking from the can. Cube, it's the volume. According to Google, it's going to be 4 point something. But we are using radius is 2, so in our can it's going to be 2. Alright, so now I'm interested in this dH dt. How fast is that going down as you are drinking when I can't spell today at all. When can is halfway full. When can is halfway full, find dH dt, the rate of change of height. All right. Which mathematical concept are we going to use here? Volume of a cylinder. Great. Volume of the cylinder. What is the volume of the cylinder? Pi r squared h. Very good. Here's your B times h. It's not a spiky object, so we don't need 1/3. Now, to find related rates, we differentiate that in respect to time because we want to see how fast are things changing. So dV dt is equal to 2 pi. How many variables do we have? Did someone just say 4? Why 2? R is constant. You see, the radius never changes here. R is constant. I'll write this in blood here. So only the variables that are changing in the physical reality of the problem, those are variables in the math translation of that physical reality. Earlier for the cone, as the sand falls on the pile, radius grows, height grows, volume grows. All of the concepts involved in our equation were changing, therefore all three are variables. In our new problem, radius stays 2 always. Therefore, it's not a variable, it's a constant, so we actually copy pi r squared because all of that is a constant to h, which is a variable, and the derivative of h is dH dt. So now we have our equation, and it's negative 20 as you take a sip through the straw, pi 2 inches squared, and we are looking for dH dt. Bless. So now what happens here is dh dt is equal from -20 divided by 4 pi, which is -5 over pi inches per minute. So the height reduces at the rate -5 divided by 5 inches per minute. There we go. Right. One more problem and we are done. I just realized that I never talked about the math ones. And these are kind of funny because problem 16 says bug on a parabola. And then problem 17 says another bug on a parabola. Which is really cool. I like those. Yeah, don't believe me. You can always read the book and you will find a lot of comical things. They have great sense of humor. Right? So there you go. Bug on a parabola and another bug.
Also, ladder against the wall again.
Oh yeah, look at that. Ladder against the wall. Yeah, you do that. I know, it's an amazing concept, right? Ladder against the wall is actually a really cool problem. It addresses a lot of physics. So this is the roof and the gutter with leaves inside. You put the ladder right here as a person standing on the ladder. Hard hat, right? Happy? Here, as I have. Cleaning the gutter.
I don't know, man. I'm still hung up on the soda can.
Hold on. And what you do is you set up the camera first, and then you go and you knock this one out. At the speed dx dt. And let's say this is a standard 13 feet ladder. You can compute how fast is this going to go down. And you can include that in the comment of the video. You see, it's useful. This section is amazing. You can do a lot with this section. So that's the ladder against the wall.
Again.
Yeah, you have your x, your y, your Pythagorean theorem, your derivative of that to give you all of these values. And you will see that because these two are added, when you move one to the other side to compute, it becomes a negative. It goes down. Everything falls in a place. It's perfect. Perfect. Every time. Now, I will work out the bug on a parabola, and you can work out the another bug on the parabola because that one has solution. So you can check. So it says a bug on a parabola. Y equals x squared. Well, this is your parabola, x squared. And apparently, a bug is moving along the right side of the parabola at a rate such that its distance from the origin is increasing. Here's a bug. It's a dot. That is at the unknown location xy. And the distance d, maybe capital D, better. The distance d that is changing in time is 1 centimeter per minute. 1 centimeter per minute. at what rate are the x and y coordinates of the bug increasing when the bug is at 2, 4? Ah, bug is actually at 2, 4, not at the unknown location. Bug is at the known location, 2, 4. And they want to know dx dt, and they want to know dy dt. Well, what I can do is I can bring this triangle down outside of the parabola. Terrible triangle. This is d, this is x, this is y, and we actually know that this y is 4 and x is 2, but we'll hold on to it a little bit. What mathematical concept can I write that would be useful to us from this particular picture? Pythagorean theorem. Because you have x squared plus y squared equals to d squared. You realize quickly that all three are variables, because as the bug is moving, the distance to the origin is changing, and the location of the bug is changing as well. So all three are variables. And when we hit this with the derivative, in time, we get all of the speeds that they want. We get 2x dx dy. We get 2y dy dx. And we also get the 2d dd dt. Now all of these 2's drop, because when you divide the equation through by 2, all of the 2's die. And we are left with x dx dy. They're looking for this dx dy, so that's cool. And then also, why did I put dy dx? What?
Shouldn't they be dt?
Yeah, dt. dx dt, dy dt. Perfect. So this is the speed in x direction, speed in y direction, the restium. And dd dt is the speed at which everything changes with respect to origin. We know that number was 1 that was given to us. All right, great. I can calculate d using Pythagorean theorem. 2 squared plus 4 squared is equal to d squared. So that's 4 plus 16 is 20. D is square root of 20, which is 2 root 5, right? 4 times 5, and 4 under the root goes out as 2. So 2 root 5 for d. If you look at this, x is given to us as 2. dx dt is what they're looking for, plus the other one is given as 4. dy dt is what they're looking for. And on the other side, you have this 2 root 5 times 1, which is dd dt. That's given to us as the distance from the origin. You see, now you have two variables there. How would you get rid of one of them?
Replace dy dt by dx dt, because y equals x squared.
Nice. That's the key. Recall, y equals x squared. You differentiate that in respect to time to get the ratio, right, to get the connection, the related rate between those two variables. And you get dy dt is 2x dx dt. And now you replace that in there. So now you have 2 dx dt plus 4 times 2x dx dt equals to 2 root 5. 2 dx dt plus, now we know that x is 2, so all of this is 16 dx dt's. Oh, actually I can cancel a 2, so that's much easier. It's gonna be 8. I've just seen that. So 1 dx dt plus 8 dx dt's, so 1 apple plus 8 apples is 9 apples. So 9 dx dt's, root 5. And we finally have that the dx dt, which is the speed in x direction, is root 5 over 9 centimeters per minute. It's a small bug. Now you plug that in there to come up with dy dt, which is 2 times 2 times root 5 over 9. And we get that the dy dt is 4 root 5 over 9. There they are. Speed in x and speed in y. Forgot the units here. Minus 10. Ta-da! Cool, right? Oh, thank you. If you want to challenge your brain, you will work on problem 19. You can also work on this stuff, right? Problem 19 is really interesting. You know that the pool, you have a shallow end and you have a deep end. This is a 3 meters deep end. So take a half of me and add on top of me. That's 3 meters. Actual ceiling. Ceiling would be about 3 meters. It's about 3 meters. So this one is a very, very nice problem to work with. Ladder against the wall. Cool thing to work with. Draining a tank. There is another. So you can put the sand on a pile, but you can also have a conical tank that you want to drain. Why would you like conical tank? It's easier to pound it in the ground. It's gone. And oh wait, there is drinking soda problem. I didn't have to bother coming up with a problem. There is the problem 30. You definitely want to consider this problem 46 for your project. There will be something similar. And where is the, did they pick it up? No? Ah, there they are. 52 and 53. Good luck. So this one took me some time. I scratched my head for some time, but I got it. I got it and I have the solution. It's really cool. Yeah, good luck on this one. If you really want to check if you're an engineer and can put the concepts together to build stuff, yeah, that's the one. The 53 I actually used when I built my theater. Works perfect. Perfect. So you can consider 53 as well as one of the spicier examples. So you have quite a few examples to work with, and as I said, 53, 52, they are really those examples that will challenge your mind, obviously for 750, but some of these are more important than another. Oh my God, another balloon story.
Oh,
It's right there.
also another fishing story.
Yeah, there's a fishing story and another fishing story. Yeah, so that's the end of this one. And